21 was a bad one. 21 was bad. So hard. But we'll talk about it. I think after I looked at it, I was like, I signed that? Sorry.
You're blocking us.
So this is, they tell us these three things are true about these statements here, or basically they tell us all three things are true. A lot of times with this, the sneaky way they do this is they don't put them in an order that makes a ton of sense. So I kind of try to go back to the basics. Is I know that I have a rhombus in this situation. So ABCD is definitely a rhombus. So ABCD is a rhombus. We know that. All rhombuses are parallelograms. So this rhombus that's also a parallelogram is ABCD. Then I know that the diagonals of parallelograms bisect each other. So in a parallelogram, the diagonals bisect each other, so that means two equal parts are formed. So that means that this rhombus that's also ABCD, it's kind of like trying to get you guys to notice there's kind of a big change here, or a big chain. So is a rhombus. Rhombus is a parallelogram. And then parallelograms have diagonals that bisect each other. So what this is kind of getting you guys to do is make that connection instead. So rather than going through this series of events, why can't we just say ABCD has diagonals that bisect each other? So it's kind of like they've said a lot of things that obviously are maybe important or you need to know, but can we make that jump to that next step? All right, that number 21 was goofy. When I was looking at like my answer key and going through that, I was kind of confused myself, to be honest. It has to do with some like programming stuff, and I don't think we actually did one of those sections that kind of showed. That was computer logic networks. We skipped that section, so I shouldn't have assigned it. It was more basically in that problem that it said that P is on, Q is off, R is off, so you just have to look at P. So don't worry about it. I won't give you anything like that. I apologize. I shouldn't have had that one in there. So I think I meant, like, I probably looked and just didn't realize I didn't cut it off. So don't worry about 21. So sorry. Hopefully you didn't spend hours on 21. It's a yes or no question, so I'm hoping you kind of made a good guess and moved on. Hours. Lost sleep over 21. All right. Questions other than that? Okay. So, yes?
I was able to answer the questions of the
What's that?
I was able to give me some questions because I was able to.
Well, maybe next time why don't you try writing your homework on like my paper, okay? Give you more space. It's okay, Cash. If you like my notebook with the answer guide, I can give that to you. All right, I'm gonna get you guys notes. This is actually our last day of new notes, and then we're getting ready for our test.
You want to see how I feel like when I'm in students class? I feel like this.
We're almost done with this chapter. If you're not enjoying logic,
I actually made it, so that was on my agenda.
Is that why it tastes disgusting? I was supposed to do this in chronological.
Okay.
We're saying thanks for I'm sorry.
Okay.
It's been a long one.
All right. So, like I said, this is our last day of new notes before we start getting ready for a test. So again, we'll review tomorrow and then test on Friday. I'm assuming that this chapter is probably going to be a little bit more in terms of, or smaller in terms of like point values. So this maybe quiz-ish test point, like smaller test points. So just a heads up on that. But we'll get into more regular math type lessons after this. When I talked to Mr. Hatfield about teaching this class, he said they always hate chapter 1, and he loved it. I mean, I don't know that I'd say that I love it, but so it's something that, I mean, he's like, I think it's important, but at the same time, it's this chapter no one ever likes. Yep.
Do we get a note card because there's a lot of vocab?
Yeah, let me find out what he's done in the past. If not, I usually tend to avoid making you name different laws and stuff. I have to see what, I'll let you know tomorrow.
Okay.
So kind of depending on whether or not I just want you to apply things, or we'll kind of see what he did. Because I'll try to kind of go off of what he's done in the past. So don't stress though. We'll make it work. Let's have something make sense here. So we're going to talk about some different ideas today. Now we're getting a little bit more into algebra a little bit today in terms of talking about how you know something is even or odd. First of all, we're going to talk about integers. You know what integers are? No. Numbers. So positive, negative, whole numbers, just basically the numbers you would use all the time counting numbers. So integers. So basically numbers. Why they don't just call it that, because there's all different types of numbers. Now, an even integer is when I tell you guys to do the evens out of a section that's 2, 4, counting up even numbers and then odds. What we're going to talk about today is how do I know if something's going to be even or odd based off of just looking at an expression. So I should be able to look at an expression and know if the outcome's going to be even or odd just by seeing it. A lot of them I should be able to tell that. And so we're going to kind of talk about that a little bit today. And they're going to use kind of the logic along with that though as well. So if I'm trying to find if something's even, so I'm going to call it n. So n is even, I should probably say that. Sorry. In my head I did. Kind of a weird comment. So n is even if n equals some sort of thing 2k. And what that means is, can I rewrite my expression so that it's 2 times something? Because if I want something to be an even number, in order to make something automatically even, I can just double it. So if something's not even, so 5's not even, in order to make sure I have an even number, I can double it and make it 10. If I have 11, I can double it and make it, so if I'm not sure. If it's already even, if I double it, what happens? It stays even. So doubling a number automatically guarantees something is going to be even. So we want it to be in that form. Now odd's a little bit trickier because I can't just like multiply something by 3 and make it odd, or like multiply it by 1 and make it odd. That doesn't really make sense. Like that won't work. So this one is kind of a little bit different because it uses the same idea, but in order to make something odd, it takes an extra step. Anyone know?
2k minus 1.
Yeah, they use plus. Look at you. They use plus, but minus 1 would also work.
Genius.
She doesn't even have her book open, but yeah. Every once in a while I have this really like amazing answer and I look at the kid like looking in his book and I'm like, seriously? So no, she was like, she said minus 1. Minus 1 also works. They use plus 1 to try to stay positive maybe. So if it's in the form 2k plus 1, so if I multiply by 2 and then add 1, it's automatically going to be an odd number. It's always going to be the case. You can think of any type of number, positive, negative, 0, whatever you want to work with, it's going to be still odd. So we're going to kind of look for those forms today. The next rule that we're going to use and know is that if m and the sum of two even integers. So if I know two things are even, so let's use so I know m and p are even. What do you know about them if I add them together? Think about adding two even integers. Yes, the sum's always going to be even as well. Yes, sum. Yeah, you used the wrong fancy word. It was good. But so he said product, but multiplication. That's also true though. If you multiply them, it's also going to be. If you multiply two evens, it's also going to be even. So you weren't wrong. So this is also going to be even. So if it's already even, so that means basically if you have an even number and then you bring another even number, it stays even. So kind of that idea with the 2k, it doesn't matter if the number is big or small or whatever, it can keep getting bigger as long as it stays even. So I'm going to show you guys kind of how this works with kind of this algebra. So looking at this expression here, this 14x plus 6y, we want to show that it would be even. And we're going to use this k idea to help us with that. So I basically want to show that this works, that any number I choose for x and y, it's always going to be an even number. So we don't know anything about x and y yet, and if you checked and you're like trying to see if you can figure something out that doesn't work, you're not going to find anything. It's going to be even. So what we can do is we can show that this actually is 2 times something. So what I want to do is I want to rewrite this using a 2. I want to show that this is double something else. You've done this before. What is this double?
7x plus 3y.
Yeah, so 7x plus 3y. So basically you just factored without being told to factor. Now, this could be even, odd, it could be even or odd, that's our only options. This could be even or odd, but once I double it, it's automatically going to be even. So once we can show that it's 2 times something, we know it has to automatically be even. Now, letter B, you might just say, well, I can't do that, so B better be odd, because that's the only other way to do this. We have to kind of be able to show it mathematically. So the idea is here, hopefully you realize that 28 plus 7, I can't like factor anything out of that. Like there's not a way to take a value out there. Like 20 and 7 don't have a common factor. So I can't do 2 times something for those two. Any thoughts on how I can show for sure it's going to be odd? we want to include that like plus or minus 1. We're going to use plus 1 even though Caitlin's idea was great. The minus 1 was fine, but plus 1's probably a little bit easier to work with here. Any ideas on how we can include plus 1 in this case? What's another way to write 7?
6 plus 1.
Yeah, we could write it as 6 plus 1. You might be like, why are you doing that? The reason I'm doing that is because I know something about that. What do I know about 28 plus 6? Yeah,
Won't it be even?
it's even already. How do we know that?
Because it's a 20.
Because it's a 20 and it's also the 6. What can I take out of those? 2. I can take a 2 out of this. And this 1, you're kind of like, why did you leave that out there? That's really ugly that way. It like kind of drives you crazy. But this is essentially that 2k plus 1. Whatever's in here is going to be odd, even, whatever. We don't care. We multiply it by 2, it becomes even. If I'm even and then I add 1 to it, it's automatically going to be odd. So understanding that to get one more place over, we've just shown that this would have to be odd. All right, kind of a strange idea, but I will tell you guys, this concept and this idea is something that ends up being applicable as you move on in math. If this is the end of your math road, then you can know this for like the next week and then, well, maybe for exams too. But like this is something I remember seeing when I was taking the college level math. I mean, being able to show and express numbers as even, odd. Do I know what it's going to be for sure? And so these end up getting used in proofs. We're not going to go anywhere with that, but that idea is there. All right, let's look at this next one here. A and B are odd, and A minus B is even. So A and B are odd, A minus B is even. And so just thinking of a single example, like saying, well, 5 and 3, do those work? And then you do 5 minus 3, yeah, it works, so that's even. But that's not an example to prove that that's the case. So you might, and it's okay to write that down and kind of think about that as an example. But rather than using those specific examples, we're going to get more, general. So what's an expression I can use that I know is odd, using what we just found out here before? Instead of A, I'm going to say A is 2k plus 1. I know for sure that's going to be odd, right? Regardless of what k is. Now I don't know for sure that B is going to be the same value, so I'm going to choose something different. Let's get crazy. Let's call it 2j plus 1. Getting wild. Hold on to your seats. I know, it's getting exciting. 2j plus 1, that looks like gibberish here. Plus 1. So we know those two are odds for sure, like regardless of what k or j is. We're going to show that A minus B is even. So we're going to rewrite this and write A minus B. Subtracting A and B. I'd have to distribute that negative in. So what am I left with? 2k minus 2j. How do we know that's for sure even? It's multiplied by 2. So I could take that 2 out, and whatever k and j are, I could, I'd subtract those. Once I multiply them by 2, they automatically become even. So kind of just understanding these values and thinking about what these different numbers look like. All right, So now they tell us a is even, and a to the third is always a multiple of 8. Again, you can think of it, use a specific example and then try some things, but we're going to try and be more general. So a is even, and a to the third is going to be a multiple of 8. So a being even, we're going to use 2k again. So in place of a, I'm going to put 2k. What do I do with that third power? Do you guys remember? Algebra 2, algebra 1. What do you do with that third power? What is this? How does this simplify?
I forgot the line thingy. It's like
Oh,
square
cube root?
but
Oh no, we don't want to solve it, so we don't want to do that. That's if you're solving it. How do we simplify this? 2k and then parentheses to the third power. What's another way we can write that?
2k times 2k times 2k.
You could write it 3 times. That would work. So, like, just real quick here, that works nicely only if it's like a 3 versus if you're taking it to like the 8th power, that'd be a big pain.
Distribute it.
Yeah, so we distribute this 3 in. So again, back to algebra 2, like rules with your exponent properties. I know you even did this in algebra 1, so, but it's been a while. 2 to the third, and then k to the third. What is 2 to the third power? It's 8. It's 2 times 2 times 2, which is 8. Questions get harder, it's okay. You're like, I'm never yelling anything out again. So we end up with 8k to the third power. How do I know that's a multiple of 8? It has 8 in it. Any value for k that I could come up with, it's times 8. So the idea of multiples are 8 is basically that 8 goes into that number. There's an 8 right there for us. So we know that anything to the third power, if it's an even number, is always going to be a multiple of 8. Kind of strange that we can know that for sure, but this is kind of how we can show that, rather than just using specific examples. So the first half of our notes, this is our section 1.7. I don't have you guys do a ton, like very formal proofs with this, kind of more like you just saw. We're going to get into 1.8 here in a minute. But this is that first half of that section. So just so you guys know with our homework, there's going to be some tied to just this part, and then we'll skip over to the other one, just so that you're not like, where am I looking for help on that? All right, do you want to finish this page before we take a break?
Yes.
Okay. All right. So there's times that arguments that people will say, like I'll say something and you're like, that's not true at all. Like, I mean, you're just wrong. Like, people can be wrong. Like, that can happen. There can be invalid, like, if-then statements. So an if-then statement can be wrong is the premises are true that are leading up to it, but the conclusion is false. So I will write that down for you guys and we'll kind of break it down here. Am I spelling that right? Premises is, no, I did not.
I think it's supposed to.
I know, I'm not. That's not a strength of mine. If it's not a word I spell very often and it's strange, I'm going to have it wrong. I think it's this. Premises. So the premises are true, but the conclusion is false. So for instance, if I said a person is a member of the band, then the person plays an instrument. Natalie plays an instrument, therefore Natalie's a member of the band. Is that true? Do we know that for sure?
Wait.
No.
So listen again, I know I should have typed this one out. If if a person's a member of the band, then the person plays an instrument. Natalie plays an instrument, therefore Natalie's a member of the band.
No.
No, so that's an invalid argument. Like kind of everything leading up to it sounds really true, but the conclusion is false. Maybe Natalie chose not to be in the band. Maybe she didn't want to play the piano for the band. So, I mean, she plays an instrument, not in the, so like, it's possible that there's students here in school who play instruments and aren't in the band. So it's possible that there's an invalid, like, argument there. So, we're going to talk about the converse error first. This is kind of a way to what these errors are. And so, like, this is kind of going back to what Caitlin was asking about. I'm probably not going to ask you guys to name particular, like, property, like, what type of error did you find? It's more that you're able to say yes or no, like, and kind of a why maybe behind it. So, let me find this here. So the converse error is basically when you confuse an if-then statement with its converse. So you use the converse, so that's our Natalie example. So you use the converse to make a conclusion. I'll show you guys what I mean with this one. Maybe this will be better. I have to see things, so. If it is Sunday, then Tim reads the comics. Tim reads the comics, therefore it is Sunday. Is that true?
The action of person reads comics doesn't determine what day it is.
Right, could he read the comics on another day? Does it say he only reads it on Sunday? No, maybe he really loves comics. So this is kind of saying, all of these things are true. That's all true. That's I'm not saying that's a lie. So if it's Sunday, Tim reads the comics, period. Let's stop there. That all sounds fine. We cannot necessarily conclude that it is Sunday. The reason they're concluding that is the converse of this statement. So let me just remind you guys of what the converse is. The converse of this statement is if Tim reads the comics, then what? Then it is Sunday. Typically, whoops, what just happened there? Typically, if the regular statement's true, the converse is typically false, or vice versa. So usually they're not both true. If they're both true, then we do that if and only if thing. So typically, if this is true, this is false. That's typically the way converse and original statements like play out. So that's why this converse idea is you can't automatically assume. Like I cannot automatically assume because you're an athlete that you're on the team. Like that's not like a fair assumption. That might not be the case. So you can't kind of flip that in that way. So Tim could be getting wild and crazy on a Monday as well and reading the comment. So just understand that inverse doesn't automatically. So this whole statement then, so this would be false to assume it's Sunday. Okay? There's a whole episode of The Office where Jim tries to convince Dwight that it's Friday, I think, so that he won't come to work the next day. And it's kind of that idea that, you can fool someone and do your normal routine Sunday. All right, so we're going to take a break then so again, this is the first part of 1.8. Do you guys want to go outside?
Yeah.
Yo. Can I nap outside?
Yeah. rest your eyes. Let's